Okay, so we have just a single capacitor and a single resistor here. So the very first thing we can find is our X of C for this guy here, C1. And that's going to be 2 times pi, which is 3.14, which we know is 6.28, times 60, times 0.2 microfarad. So that'll be 0.1234562. So 0.2, the decimal place would be here, and to convert it to mics, we would go from mics to farads, we go 6 over, so that's the right value. We'll divide that into 1, and X of C1 is going to equal 13.27K here. So let's write that down. X, whoops, not with yellow though. Let's undo that. Let's go pink. X of C1, 13.27K. So that's X of C1. Now, we know our total, it's 5K. And in order to get our Z total, we need to get a total impedance of this circuit to be able to get the value we need. So let's calculate that. So Z total is this nice long complicated formula. R total plus X of C, in this case X of C1, because it is X of C total because it's the only one, over the square root of R total squared plus X of C squared. And this should be a times, so let me fix that for you because I did plus. And it is not a plus, it is a times. And that can change everything. So, the ZT is now equal to, R total is 5K, X of C1 is 13.27. Let's do that math, shall we? So 5 times 13.27 equals 66.35 on the top half of our equation. So let's write that down. 66.35. On the bottom, we're going to have the square root of 5 squared. I can do that in my head. 5 squared is 25 plus X of C squared. Well, we know X of C squared is 13.27. So let's go ahead and square this guy. 13.27 squared, 176, and we'll round it to 0.1. So it's 176. I can get my marker working here. 176.1. So ZT is equal to 66.35 over 201.1 if I'm doing my math right, but we'll double check me because I don't want to, and I got to get the square root of that even. So let's add 25 plus 176.1 equals 201.1. And again, I forgot to put the square root symbol there. So let's do that, lest I forget. So it is under the square root. I know it's kind of all, let me use a different color so you can see that. So that is 66 divided by the square root of 201. So we'll get the square root of that guy. It is 14.18. So let's come down here and let's write in ZT is equal to 66.35 over 14.18. So let's do that math. Clear 66.35 divided by 14.18 equals 4.67. So let's come back up here, 4.68 when we round. Let's get rid of all these things. 4.68. Sorry, this takes a minute to erase. But let's write it right here and we'll keep it in pink. So let's get a pen. So ZT is 4.68K. So that is our overall impedance there. So let's get rid of the rest of the stuff just to make our lives a little simpler, shall we? We'll get away with all this rhetoric down here. All right. So now we can easily calculate IT. It's just going to be a matter of taking the applied voltage, 120 volts, dividing it by this ZT, and we've got IT. So 120 divided by 4.68 gives us 25.64 milliamps because we did it by the K value. And now IR is going to be equal to 120 divided by 5. 120 divided by 5, and that's 24 milliamps. And I of C is going to be 120 divided by this 13.27. And we come up with 9.04, even if we round, milliamps. Both of these should be in milliamps. So obviously we can't add these two. We know that already. We'd come up with 33.01. That isn't right. But we can double check our IT. Basically, we square this guy, add it to the square of that guy, and get the square root. So all I'm doing is saying 24 squared plus 9 squared equals, you can get the square root, 25.63. Very little error there even in the rounding. So we're spot on. So just remember, when calculating values for RC parallel circuits, R and X of C are not in phase. IR and IC are not in phase, and that's why we have to do these fancy formulas to get it. And then we have power, and I'll let you read this slide on your own. So that's pretty well everything with RC parallel circuits. Hope this has been some help. There's some practice problems, your chance to shine, but if you hit a brick wall, as always, let us know. We'll be happy to help.